Yeah, my pleasure to introduce an old friend and colleague as opposed to a new friend and colleague. The old friend and colleague is Professor Sijian Wang, who is a member of the Institute for Quantitative Biomedicine and also an associate professor in the Rutgers School of Arts and Sciences Department of Statistics. And he's going to provide us with a primer on artificial intelligence and specifically to talk about the statistical underpinning and to elaborate more on the vocabulary that Minkyung has so elegantly described for us. Sijian, the floor is yours.
Thank you, Stephen. Thank you for the introduction. And hello, everyone. So I'm Sijian Wang. So today I'm very happy to give a primer on the artificial intelligence from a statistical point of view. So as a statistician, often when I give a statistical talk, I worry that audience may find it boring and leave. But today I have no such a concern because Stephen's talk is next. So I'm sure many people will stay here. Okay, so then the first question probably is, what is the artificial intelligence? So this is probably a sort of a hyped picture or description that gave people a feeling like AI is very fancy and very complicated. So today I'm going to introduce AI vocabularies and also some statistical illustration. So I hope I can make people believe AI is actually, everyone can understand and everyone can use it. So first is a AI chart in terms of techniques AI use. So this is based on my personal understanding. So it has the machine learning and which includes the deep learning, which is very popular model recently. And also it has natural language processing, mainly for the language data or the sequence data, as well as the computer vision, like for the image. And also there is a popular item is robotics, but that will not be the focus today. And you can see here, I separate the machine learning from NLP and CV. So actually NLP and CV use lots of machine learning models, but they also have their own sort of specific procedures and techniques. That's why I separate them, put them separately. And also it's very interesting that actually protein structure is naturally related to all of these three things. So it's naturally fit to solve the protein structure problems, because for a protein structure, it can be viewed as a 3D picture or 3D image, or viewed as a graph or a network, like each amino acid or even each atom is a node, and sort of all kinds of interaction between the two are edges. Also, we know that protein is a amino acid sequence, so it can be also viewed as a sequence data or treated as a sentence or paragraph or article. So that means that the methods developed in the CV and NLP can be naturally applied to the protein structure problems. Okay, so then the next I will illustrate some AI vocabularies. So the first one is a popular term, machine learning. So what is machine learning? It is about the prediction. So it actually has a long history. So here are two examples. And also machine learning can be also viewed as a reverse engineer. So actually for our traditional programming, we have data and we have rules. We just use a machine or computer to implement them to get the output. But for the purpose of machine learning, it's the other way around. We have the data and also the output. We want to figure out what are the rules underlying this entire process. And if I further decompose machine learning into two parts, that's one is machine, which essentially means a model. And the model usually specified by a set of parameters. And the learning essentially means the data plus the algorithm to estimate the parameter and use the model to predict for the futures. Here I also want to emphasize the importance of using the good data. So everyone knows how important data are, but not everyone is careful enough with data used. So a bad model with good data can easily beat a good model with bad data. So here I quote one sentence from Mark Twain: "It isn't what you don't know that gets you into trouble, it's what you know for sure that just isn't so." So I really want to emphasize on the importance of having the good data always, check the data. Then the next one is a model. So what is a model? Certainly it's not as beautiful as this, but not as boring as this either. So from a statistical point of view, essentially a model is a set of assumptions. So the assumptions about the formats of the relations between the outcomes and the features, or the assumption about the formats of a feature's effect. And some assumptions can be validated using the data, but some assumptions cannot be validated or verified. That's why they are called the assumptions. And also some assumptions can be very subjective. So the machine learning models or the AI models can be subjective as well to certain extents. And also all assumptions models have potential risks. So then it's better to be aware of this and carefully check the model, check the output. So here I also quote a famous saying in statistics: all models are wrong, but some are useful. The last thing I want to say about the model is the model interpretability. So it is very important. So for many of you heard like a black box and a white box. So if a model is interpretable, then it's very helpful to sort of encourage people to use it. And also it's much better for us to figure out the reason when the model performs badly, and also understand the reason when the model performs greatly. So then the next vocabulary is features. Sometimes it's also called attributes or variables. So the features are the representation of the data. They are used to fit the machine learning models to estimate the parameters. And if we treat the machine learning model as a car, then data are like a raw oil and the features are like gasoline. So it's refined raw oil. Many times we cannot use the raw oil directly. We need to use the gasoline. So then the features are actually quite important. So here is an example. Suppose we want to distinguish between the apple and orange. We can consider two features. One is color, the other is weight. And using these two features, actually we can separate the apple from the orange by, say, a single line. But if we choose like a different feature, say if we choose two other features, number of seeds and the ripeness, then we cannot distinguish apple from the orange. So that means we really need to pay attention to which features we are going to use. We should use the most informative features for our task. And in practice, the number of features can be very large. Say the deep learning model can easily have 10,000 features. And more features not necessarily lead to a better model. So the signal can be overwhelmed by noise. So we still need to be careful about what feature we're going to use. And also the same feature can be informative for some tasks, but non-informative for other tasks. So there is a important subject called the feature engineering, which means we create the useful feature, informative feature from the data. And here I want to emphasize the importance of domain knowledge and human experience to create the useful features. Say, for example, people find actually BMI is much more effective in many tasks than using the weight and the height separately. So the next vocabulary is underfitting and overfitting for models. So the underfitting means that the model doesn't capture the full complexity of data. So here is an example. Suppose data has this kind of up and down trend, but if we just use a simple line to capture the trend, then it is an underfitting. So it's it doesn't capture this variation in the data. And the overfitting is the other way around. We tune the model so carefully so it starts matching the noise in the data. Say, suppose this is my data, it looks like a sine function. But if I just connect each of two dots, we will have this very sort of unsmooth curves. So then it's a example of overfitting. A better one probably will be just a sine curve. That's a good balance between the finding the trend and also against the noise. And another vocabulary, two vocabularies are the bias and the variance. So the bias usually measure how large the prediction is from the target or is related to the accuracy. And the variance measures how stable the predictions are. Like if you give a model several tasks and whether it's always perform well or sometimes perform well, sometimes it performs very well, sometimes it performs very badly. So here are some examples. So this is a ideal case. It has the small bias. You can see all of the dots are close to the center, and it also has a small variance. And this one means it has a large bias, so it's further away from center, but the variance is kind of not that large. And for this one, actually, you can see it's scattered, but all around the center. So this is a little bit counterintuitive, but this one, for this one, the bias is actually small because the bias is in the sense of averaging. So if you average these points, it's very close to the center. But the variance for this one is very large. And this is probably the worst case, have a large bias and also the large variance. So you can see both bias and the variance are bad. So we want to actually reduce both of them. But in practice, that's not that simple. So usually we are facing a so-called the bias variance trade-off. That means given a same data and also the same model, usually we cannot reduce bias and the variance simultaneously. So we need to take a trade-off. And for the final prediction error, here means mean square error. It can be showed as it has two parts. One is a bias, square of a bias. Another is a variance. So in practice, it's quite often many like deep machine learning model, including the deep learning model, we actually increase the bias a little bit, but reduce the variance greatly to achieve a better performance. That means to achieve a smaller prediction error. And also the two words appear quite often in AI is a supervised learning and unsupervised learning. So the supervised learning just means we have some like we have a teacher to teach the model like what is right, what is wrong. But for the unsupervised learning, that means we do not have any sort of a standard, a gold standard. We just want to find some pattern in the data. And for the related to the supervised learning, there are three very commonly used words: training data, validation data, and test data. So here, the training data just means the data we are going to use to train the model. And the validation data is the data we use to tune the model, like to select the so-called tuning parameter. And for the test data, that's some data, for the first two tasks, training and the validation or the tuning have never touched. So then that will serve as an honest object to evaluate the performance of our model. So if we evaluate the performance of model on the training data, we will have very likely to have an overfitting phenomenon. That means we can tune the model very carefully to match the noise to achieve the perfect performance on the training data. But then when we apply to an unseen test data or future data, the performance can be very bad. So then the next I will give a browse of machine learning models used in the AI. So this is a general sort of a picture. So the center is a machine learning. It has the classical learning methods, ensemble methods, neural net, and the deep learning, also the reinforcement learnings. So here is a further breakdown of the type of machine learning. So for the classical machine learning model, usually is applied to like relatively simple data and also with clear features. And for the ensemble learning, the case we use this method is when the quality of a sort of a model is a sort of has certain concern. So we want to use many models to sort of borrow strengths from each other and to combine the strengths of all the model to achieve a better performance. And for the deep learning, that is usually for the complicated data and with some unclear features. And here also has a belief in a miracle. This is just means actually right now for the deep learning, there are still lots of open theoretical questions. We actually do not fully understand why the deep learning works so well, but just to have a convincing observation, it works very, very well in many applications. And the reinforcement learning is a little bit sort of special, different from others. So it doesn't require data. we have data to train the model, but we just have an environment to interact with our model. So it's more like a adaptive way to build up the model. And for the classical machine learning model, it can be further decomposed into supervised and unsupervised. And for the supervised learning, we can have a classification problem, which means our outcome is a binary or a discrete variable, like whether an email is spam or not. And regression means our outcome is a continuous, like if we want to predict our, say, the income, if we learn certain like techniques, like after learning AI, how much more money we can earn. And for the unsupervised learning, that means we do not have any outcome. So we have we can do the clustering. That means separate the data into several parts and to capture a certain pattern. And we also have a dimension reduction method like a principal component analysis or PCA or the TSNE, which is used quite widely in the deep learning related problems. And also the another one is a association study. We just want to find like many things will appear with another set of many things. So then the next one is for the regression. So here is an example. Suppose we want to know like the relationship between the hour, the time, and our traffic time, traffic condition. So here each dot means a data. And for the regression, that means we can just fit a line. Yeah, so you draw a line through the trend, through the dots to try to capture the trend of the data. That is actually a machine learning, simplest machine learning. But for this example, you can see a linear model or a linear line may not capture this trend well. So then we need some nonlinear models, like we can use polynomial to fit the data, then we can have a better fitting. So the next one is a naive Bayes. This is for the classification problem. Suppose we want to distinguish between the spam and the regular email. So this naive Bayes is mainly based on the so-called the Bayes theorem to do this classification. This is a very simple method, but it's actually used widely. Like until the 2010, the naive Bayes is actually the major method for this spam filter. And then the next classification method, popular one, is K nearest neighbor. So here is an example. Suppose we have the training data, we have a diamond and we have a star, and we want to predict which class this heart should be. And then the idea of a K nearest neighbor is that we just draw a neighbor close to the heart, and we see how many diamond we have in this neighbor and how many stars we have in this neighbor. So for this example, we have 2 stars, but only 1 diamond. We will predict the label for this heart to be the star. And the next one is a support vector machine. So that is the idea of this. It's also for the classification problem. So the main idea is to find a so-called the hyperplane to separate 2 sets of dots. And then we want to find out this hyperplane to have a so-called the largest margin or largest buffer. You can see this line is equally further away from 2 sets of dots. So that is sort of give us the largest buffer to correctly predict the points into the correct class. And for the points on this dashed line, that is called the support vector. And the reason it's called the support vector is we can show that actually the final performance or prediction is only depends on these support vectors. So then as a consequence of this, support vector machine is very robust. So it's robust for the outliers. So if you have some points here and some points here, it doesn't affect your model. And another very popular classification method is a classification tree. So it's just use a tree style rule to do the classification. So here, suppose we want to decide whether to give a loan to a person. We first check the credit history. If it's good, go to this side and further check whether the person has a debt more than 1,000. If no, then give the loan. Now, if yes, then decline the application. And if the credit history is not good, it's bad, then we will look at other criteria like whether have a pledge, also whether has a guarantor, so on and so forth. So you can see from top to end, it tells you a decision a rule how you reach this decision. And also because the whole rule has this tree structure, so it's called the classification tree or the decision tree. And then the next popular method is the random forest, which can be viewed as a extension of a classification tree. So shortly speaking, random forest is just to grow many trees and get an average for the final output. And further, for each split in each tree, the random forest randomly select a subset of features to be considered. So the reason it's called a forest is because we grow many trees, and the reason it's called has the random here means we randomly select some features to build up our model. And a related method is called the boosting. So it's also grow the series of simple trees. But the difference from random forest is these many trees are built up sequentially. And for each tree, we actually adaptively reweigh the importance of data points to enforce the new tree to correct the mistake made in the previous tree. And at the end, we just do a weighted average of all these trees, so it can be shown to guarantee to have a much better performance. And we also have the general model averaging. So like we introduced like nearest neighbor, decision tree, support vector machine, we can fit each of these model on the data and do an average. So we hope just to borrow the strengths from each other and also combine the strengths of all of this model to achieve a better performance. So then the next one is about the clustering. So the clustering, as I mentioned earlier, we do not have an outcome here. We just want to seek for a partition of data into distinct groups so that the observation within each group are quite similar to each other. And also observations belonging to different groups are quite different from each other. And from this current description, you can feel it's quite crucial to define what is a similarity and what is a dissimilarity. Actually, for the definition of these similarities heavily depends on the problem itself and also the domain-specific consideration. So this is a hypothetical example. Suppose I have these 6 objects. I want to do a clustering. So then the question is how many cluster and what are these cluster? So according to the different criteria, we can actually have a different clustering results. All of them make sense. Say if we cluster defined by the shape, we can put the top 4 as one cluster, bottom 2 as another cluster. But if we define by the fruit or non-fruit, we have a top 3 as one cluster and the bottom 3 as another cluster. So both make sense. So then it's crucial in practice for us to define what the similarity mean before doing the cluster analysis. And in general, there are 2 ways to do the clustering. One is a hierarchical way, also called the bottom up. Another one is a partitional approach. It's also called the top down. And for the partitional approach, the most famous method is called the k-means. So it's a iterative method. So first is randomly separate the data points into groups and get the center. And then it's assign the cluster membership to the points and with a criterion that for each point, it should be assigned to the cluster with the smallest distance to the corresponding cluster center. And after doing that, we can redo the cluster center and then reassign the cluster membership until convergence. You can see at the end, we can have a quite good separation. And for the hierarchical clustering, it's a bottom up. That means we first look at each pairwise distance, like or pairwise similarity. We want to pick up the most similar pair and combine them into one cluster. And then we treat this cluster as a single point and then further evaluate the similarity among the points and find the next most similar pairs and combine them. So then we just keep moving up until like all points can be considered as in one cluster. Then we can decide where to sort of cut. If we start cut here, we will end up with 3 clusters. And for the association rule learning, the most famous example is a diaper-beer relationship. In the grocery store, people usually put the diapers and the beers together, but it doesn't mean there's any causality or connection between the diaper and the beer. Just the people buy the two things quite often. So the association rule learning is just try to identify this kind of many relationship. Like many people buy diapers, they also many people buy the beer at the same time. So then the next one is deep learning. So this is a simple illustration. So here using the deep learning language, each circle is called a node, and each column is called a layer. And each node is actually just a feature. So for the first layer, the feature are just the original inputs. And then for the follow-up layers, for each node, that is the linear combination of features in the previous layer, then apply a nonlinear transformation function, which is called the activation function. And you just keep doing this, you can have many layers, because that's the meaning of a deep. And at the end, we can have the output and do the prediction. And you can see here, because each node is a linear combination, each feature is a linear combination of all features in the previous one, and also apply a nonlinear transformation, it can consider a very complicated interaction patterns. That's what makes the deep learning very powerful to make the good prediction. But this deep learning illustration is just a general deep learning model. It just doesn't require like data has any specific feature. But according to the specific feature, we can have a special deep learning model. One is convolutional neural networks. It's mainly for the image data. And the key thing here is called the convolution. So the convolution, roughly speaking, is a local averaging. And you can see here, we just weighted average of the points in color. And the reason we can do the local average here is because in image, usually we have this kind of a local structure. Say, for example, if my input is a cat, and for the first step of this local averaging, we'll get this sketch. And then for the next layer of this local averaging, we hopefully can get like the eye, nose, and the ear. And these are very informative features, can help us distinguish, say, cat from the dog. So because of this local structure, then the local averaging can be very helpful to build up a good predictive models. And the next special class of deep learning model is recurrent neural networks. It's mainly designed for the language data or the sequence data. So here it's just utilize this sequence characteristic. So here I use an example. Suppose we have a word hello. We can decompose the hello into 5 words, and there is a special order here. H is the first letter, E is the second letter. And for the recurrent neural network, it just go from the beginning to the end. And in each step, it's not only capture the information at the current stage, say here, not only capture the information in the current stage, it's also remember the information in the previous stage. So then if you keep doing this at the end, you actually accumulate all of this information. But there are most traditional recurrent neural network may not have a good performance because especially when the sequence is long, if we keep remember what happened in the past, it may decrease the performance. It's just like good athletes, they will actually forget the failure, the history, but also remember the lessons they learned from the failures. So then to improve their performance. So that means for some information, we should remember. And for some information, we should forget. And just utilize this kind of spirit. There are 2 kinds of methods. One is a gated recurrent unit, a GRU. Another is long short-term memory, LSTM. So they actually shown to have a greatly improvement over the traditional recurrent neural networks. And later, people find that these 2 methods still do not have a good enough method for some complicated problems. Then people actually get this attention idea. So the attention is just to get the similarity between any two units, but here is actually asymmetric similarity. And based on this similarity, further do the deep learning model, actually the multi-layer neural network, that is called the transformer models. So nowadays, the attention-based transformer model is shown to have a best performance. So the next one is the reinforcement learning. So it has the agent and the environment. So this is the agent need to make the decision, and this is the environment. So each time we will have an observation, receive an observation from the environment, and we need to make an action. And after making the action, we will get a feedback from the environment as well. That's called the reward. So we just want to develop the model or figure out the procedure to maximize the reward in the reinforcement learning. And also you can see here, the data is actually generated adaptively because the data you're going to see depends on what action you chose. And the fundamental problem in the reinforcement learning is exploration versus the exploitation. So here I use an example. If I want to go to a restaurant, I want to decide which restaurant I should go. So then there are two choices. One is go to my favorite restaurant. This is called the exploitation, because it's based on my current experience. So the good thing is I will guarantee to have a good experience. But the bad thing is I may miss some restaurant. I can even like it, more than the current most favorite restaurant. And another decision is to try a new restaurant. This is called the exploration. So for this one, it's possible we will go to a very bad restaurant, have a bad experience, but it's also possible we just discover a restaurant we like more than the current most favorite one. So then the key thing, the core thing of reinforcement learning is to find a balance between the two to achieve the overall maximum rewards. Okay, I think it's about the time. That's all I want to talk today. Thank you.
Thank you very much, Sijian. Great talk.